Yeah, welcome everyone to today's session. So in today's session, we'll be talking about scaling the RAG and embedding computation with Ray and Pinecone, together with my co-speaker, Ray from Pinecone.
Thank you. Okay, so my name is Roy. I'm an engineering manager at Pinecone. I've been with Pinecone for 2 years, so I got a good experience of pre-ChatGPT AI era. Previously, before Pinecone, I worked in data engineering, ML engineering, mostly Spark, DBT, entity knowledge graph, those kind of things.
Cool. Hi, everyone. My name is Cheng Su. I'm engineering manager of the data team at Anyscale, which is an AI ML platform company. Before that, I was spending a couple of years in the data infra organization in Meta, working on Spark and Hadoop. So here's today's agenda. In the first step, we will talk about the introduction about the problem we are trying to solve, and we introduce the RAG, which is the retrieval augmented generation concept, and we talk about what is vector database and what is embedding. Just briefly go through the concept and what is motivation. In the second part, we will talk about Ray and Anyscale. What's Ray and Anyscale, and how do they do the embedding computation and the large language model offline inference on Ray and Anyscale. Lastly, we go through the Pinecone, introduce the companies, and go through the serverless architecture, talk about how it can scale up and cut the cost for the vector database, and we discuss the quality of the RAG versus training. So the problem, what did we try to solve together? We want to evaluate the quality of a RAG solution in large scale. So the data we are using is a really large scale, like Pinecone refined web, which has 1 billion documents from the Common Core, which is a public open source dataset. And the embedding model we are choosing is GT large, which is also a popular embedding model, which has a dimension of 1024. In the first step, we reading the data, process it, and embedding with Ray. And after getting embedding, we do the batch uploading and indexing on the Pinecone serverless. And then we run a large-scale RAG evaluation on top of the data. So here, let's get to introduction of the RAG by my co-speaker, Roy.
Thank you. Okay, so I'm not assuming you know anything, so I'm going to start from the beginning. That's my, I made up this equation. I see RAG as you're trying to get data to your language model, but not do training, okay? And I'm gonna try to convince you with two things. One, you wanna do RAG because LLMs don't know what they don't know. And two, they tend to hallucinate even when they know the answer. And I wanna convince you that RAG will solve those problems by providing the models with actually factual correct data. Obviously, there's a small star there. You have to have good retrieval around. So I want to convince you with these two things, right? So let's start with an example. I made up a form of art. Okay, that's a made-up name. And I asked ChatGPT about the most important thing about this new form of art. So obviously, you'll get something like, I don't know, right? Or isn't a widely recognized term in the traditional art world. Great. Obviously, if I add some context and I ask ChatGPT to make up some context around like this Monterflugel art form, then the model will know everything, right? So that's a very simple, very dummy case. But obviously, LLMs don't know what they haven't trained on. But sometimes they hallucinate, and that's a bigger problem, right? Because I'm asking the same question, I'm getting an answer that sounds really convincing, right? Combining surrealism, abstraction, creating visually striking, yada, 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 right? That, I'm convinced. And if I don't understand anything about art, I would take it as the truth, right? And it's not only when you make up stuff and try to make the model fail. Also, if you just ask a simple question. Now, that's a confusing question. I'm using it a lot in my demonstrations. But generally, right, I'm asking what's the third tallest mountain? And here it got confused. It gave me the first tallest mountain, okay? It happens a lot. Now, you might say, okay, you made up the question. It's not formed correctly or something. But if I only give it like the context, it will figure it out perfectly every time. Right? It's the same question, same type of reasoning I need to do, but now I only gave it a context it already knows, right? And the way I like to think about it is that we want to solve, the way to solve the problem, the way to think about the problem, is that LLMs generate tokens in this kind of probability process, right? And sometimes they will take a turn left and another turn left, and they will go into the hallucination realm. When we're providing context through RAG, what we're actually doing is we are moving kind of we're moving them more into the right place, more into the contextually factual correct area. And this will make them hallucinate much, much less. Also, I want to convince you about the energy around that, right? So the GPU per million tokens is way, way, way larger than the retrieval per million tokens and the GPU for 10K tokens, right? And the quality, I hope to convince you with that, is about the same with some error, which is okay. And we actually tested it, and you get around 95% of the accuracy for 25% of the cost, even in small context sizes, okay? So it's also a matter of cost. When you want to scale a system, it's a lot about how much does it cost me. So let's talk a little bit about vector DBs, embedding, how is it all connected? So that's the most simple diagram of RAG, right? I'm taking my data, passing it to an embedding model, storing it in some database, and then when I have a question, I pass it to the embedding model, getting things from the database, giving it to the model gives me an answer, right? It's a very simple thing. And for a good reason, this is actually went out, I think, today, a couple of hours ago, State of the Data and AI from Databricks. I really encourage you to read the report. Vector databases are in crazy growth, right? And for a good reason. But what are we actually doing here? Embedding, so if you don't know, embeddings is basically just a way to take unstructured or a piece of information and give and assign it with a coordinate in a high-dimensional space, okay? And why does it matter? It matters because information in the real world looks like this, right? So medical form, I don't know, a legal document, a 10K of a company. This is what information is, right? It's not all tables. You know what? It's mostly no tables. And then a vector database is a type of database that is designed to perform this kind of a similarity search over large corpuses of unstructured data, right? And the way to do it is using geometric methods like clustering or graph to efficiently scan the space, okay? It's a scaling problem again. And there are other use cases, so it's not just RAG and AI applications. Semantic search was really big before ChatGPT hit, right? So search applications, classification, candidate and training data. This is a really interesting one. Actually, we see also in the LLM space, a lot of companies, what they do is they ask a vector database to generate examples, and then they use those examples for few-shot learning or prompting for LLMs. And the way we kind of combine the two technologies is basically to say, hey, Ray can help me scale embedding and processing for large data sets. And Pinecone and the serverless architecture, I mean, actually searching over billions of documents. Right? This is what we try to test. And in short, this combination will give you the scale for what we call modern enterprise RAG. So it looks like this, right? So basically, for the embedding, for the processing, I'm going to use Anyscale. For the vector database, I'm going to use Pinecone, and we're going to show you the result very soon of this kind of experiment we ran together. But let's first talk about Ray, Cheng.
So Ray is an open source project that first convinced at the University of California, Berkeley in the REST lab. Coincidentally, this is also where the Apache Spark was also born. And this remains an open source project. And the goal for the Ray is to build in the open source operating system powering the AI application. In 2019, Anyscale as a company was founded by the creator of the Ray to build the fully managed platform for the Ray to make the toughest problem in the distributed computing easier, mostly targeting the Python AI applications. This is just a short history of the Ray. In 2020, Ray version 1.0 got released. 2022, 2 years later, 2.0 got released and invented the Ray AI libraries. I will get into the detail of what is Ray AI libraries. And in 2023, Ray community already built a lot of improvement around LLM and AI infra. Ray as an open source project already have 30,000 stars on the GitHub and hundreds of contributors across the world. Here's just a very short list of portfolio of the Ray users across the industry. The name, some names were called like OpenAI and other companies are using leveraging Ray technology to building the large language model and AI applications. Some metrics about Ray that's being adopted in the industry, such as the number of the downloads from the pipeline compared to the several open source popular libraries, and also the GitHub star history, which is increased really quickly in recent years. Let's get to Anyscale, which is the end-to-end AI platform for the AI companies, which has optimized Ray runtime, and also have built a lot of developer tool around the Ray and support the security and governance to run the Ray in a security way, and also have a lot of integration with the ecosystem, which for one developer, you can go through the development, processing data, do the model training, model fine-tuning, deploying the model, and doing serving all in one platform. Holistically, how Ray address the AI and LLM challenges, which is have the Ray core as a distributed layer for the heterogeneous distributed computation. On top of Ray core, a list of the libraries has been built, such as Ray Data for the data processing, Ray Train for the distributed model training, Tune for the hyperparameter tuning, reinforcement learning, and Ray Serve for the model serving. And it supports all the public cloud providers such as AWS, Google, and Microsoft. In this session, we mostly focus on the Ray Data library, which is a scalable data processing library for the ML workload. Here is the link for the open source documentation. So the first use case of the Ray Data focus on is offline batch inference. Offline batch inference often means you have a pre-trained model or a list of the models, and you have lots of large-scale offline data. And people want to use a model to do the inference on the large-scale data. So one first use case is large-scale unstructured data processing, such as people have the images, video, audio, text. They want to do the video to the text, image to text, all these kind of different model inference. So Ray Data is built in to get the best performance of that. And also it supports the RAG embedding generation and LLM offline inference. I will get into in the next several slides. Here's a benchmark for the unstructured data, which is a typically workflow for how to do the offline batch inference. On top of Ray Data, user write the applications. The first step is loading the data from the cloud storage and do the data preprocessing, such as some images need to resize, recrop, or like some tests need to be cleaning. This all down the CPU cores. After that, the data will be moving into the GPU, do the model inference. And after get the inference results, the data will be read out either in the cloud or in the local file system to save on the storage. And the whole process can be scaled independently of each stages. And each CPU and GPU can be scaled independently. So here's the benchmark we did, compare the Ray performance and the cost to process 1 million images doing the image-based batch inference versus some leading open source framework and ML platform. And here we give the link for the full blog post. So the second use case is do the distributed model training. For the distributed model training, data loading always been the biggest pain point. People do not know how to load it, sharding the data, how to parallelize the data for the model training. So Ray Data provides a scalable distributed training data loading and the preprocessing functionality. It supports all the popular deep learning frameworks such as PyTorch and TensorFlow, which can be done in the Ray Data plus Ray Train. The Ray data in the PyTorch ecosystem, which is being called in the PyTorch conference last year by the speaker from the Meta, which that Ray data is one of the solutions in the PyTorch ecosystem for the data loading. So why Ray data? So inside Ray data, several major features has been built out to really do the efficient ML application. The first one is streaming execution. So the data is not all loaded into memory in once, which may cause a memory problem, out of memory issues. So all the data is reading and processing in a streaming way, which allows to scale out to the petabyte scale of the data. Secondly, it supports the heterogeneous resource requirement. So for example, there's a lot of CPU nodes plus some like GPU nodes. All the resources can be used together. So also if you have different hardware accelerator of the GPUs, they all can use in a same cluster without problem. Thirdly, it supports automatically failure recovery, which is very important when people run a workload on unreliable clusters, such as spot incident to save cost or some like process node cluster failure. And it also supports a large variety of the data source and formats, such as AWS, S3, Google GCS, Microsoft, or any like local development file system. And it supports the Parquet, unstructured data, image, video, audio, JSON, or the vector database format. And it has a Python native and a seamless integration with other ML libraries you can use together with Hugging Face dataset to download the Hugging Face data and then do the model training or do the inference. Here's the 1 billion embedding benchmark we did with Ray and Pinecone together, which we think is the cheapest solution in the market right now, costs $6,000 on Anyscale. Let me get to the detail. What's this benchmark? First section is the input data. We use, as we speak, we use the Pinecone Refined Web, which is massive English web dataset built by TII to train their large language model. The on data size 1.6 terabytes for the whole data, which looks small, but if you look at the embeddings, it has a 1 billion embedding. And the embedding model, we use a GT large to do the model embeddings. And the Anyscale job, the whole embedding computation and injection into the Pinecone servers contain like 320 810G AWS G5 instance, which is most like affordable GPU type that people can use. And the end-to-end processing time is 18 hours. So how to do the embedding underneath? We summarize as a 4-step approach, which also applied outside of Ray. The first step is doing the reading, that reading the input data from cloud storage, either in more than terabyte scale or the petabyte scale, and also different data format. People can have PDF as legal document, Word, Microsoft Word, text, JSON, Parquet, all different formats. The first step is reading all these different data from the cloud storage into the cluster. The second step is doing the chunking. So what is chunking? Chunking is splitting the text into smaller sentence or sub-sentence, which allow like the embedding model to convert to the tokens. So here's like open source tools such as LangChain or Llama Index text splitter to do the work. The third step is doing the tokenization and the embedding. Often the sentences after chunking need to be converted into the tokens that the model can understand and use the embedding model to generate the embeddings. Some embedding models such as GTE we use, also there's other embedding models all available on the Hugging Face. The last step is writing to a vector database. The batch is required the batch upserting the embedding results for best performance without like causing too many RPCs to the vector database, and also along with other metadata such as what is the embedding original text and what is the IDs of the embeddings. Here's the workflow in one picture, how it's look like. The raw data from the left is being reading into the CPUs in the Ray cluster and do the chunking. During that, after getting some batch of the chunking data, it's sending to the GPUs to do the model inference, model embedding. After that, getting embedding result is sent to some like CPU cores to upsert into Pinecone vector database. and the whole workflow is done in a streaming way. So without like waiting for results from each other stages, each stage can run in parallel concurrently. Another topic is after you get the embedding and get the vector database, you have to do the LLM inference. So currently there's two choices, offline or the online, that is the question. So most people go with online inference right now, which is what called model serving. The most popular solution in the industry right now doing the API endpoint. Either do the GPT with OpenAI or other like Bedrock, Anyscale to do the API endpoint. You just hit the endpoint, ask a question to the LLM. Here that is really optimize the latency, which is you get the real-time result for the prompt or you want to interact with LLM. So you should choose this solution if you want to optimize the latency of the inference to be as fast as possible. So the second category of the inference, what we call the offline inference, which is often done by a batch job. So OpenAI has the batch API. Anyscale also have a job API, which you can submit a job to optimize the throughput of the resource usage. So you should choose this if you want to scale up your workload to a large-scale data set and you have a very tight budget. So doing the offline inference will give you like a better throughput, but with least cost. Example of use case such as you want to run some daily or the hourly job to process large-scale in-house offline data. You don't care much about the real-time response, but you want to get in hour or the days, like test summarization of a large-scale test or do the user's information processing. That's all suitable for the offline inference. Okay, let's get deep dive into the Pinecone by Roy.
Thanks. Okay, so I want to talk a little bit about the Pinecone side of the things. So in general, Pinecone, we also started in 2019, so way back. A lot of people, a lot of customers. We launched serverless in January of this year. And we also developed an open source RAG framework. But generally, we're working on more exciting products in the field. And I want to talk about serverless because this is kind of, we're talking about scale, we talk about how to do billion scale RAG, and how the serverless architecture really enables everything. And listen up, I'm going to give you all the secrets and then you can go and build your own vector database, I promise, okay? So let's start. First, you need a dynamic clustering algorithm. So what we did at Pinecone is we actually developed our own algorithm. So a lot of vector databases are using kind of off-the-shelf, HNSW, if you know, or other type of algorithms. We developed our own algorithm that does clustering in a dynamic way, meaning as you ingest data into the system, it will recluster to optimize for search, right? Such that in query time, we know exactly which clusters to hit. So it scales much more efficiently, okay? Almost like the square root of your the number of vectors you put in. Second, you need to separate read and write, right? So this is very common if you're building data infrastructure, always separate read and write, right? Such that you can utilize the system for query even if you're ingesting, okay? Now, one of the key things here is also to add freshness layer, okay? Because this reclustering of the algorithm and the fact that you have this kind of write path structure really means that you need to have a fresh layer. So we added the freshness layer. Then what it does, it gets the data as it flows into the system. So the data is available directly, instantaneously for querying. And then the system automatically will take it in and start clustering it and rebuild the clusters. So we keep kind of we want to keep the P95 for queries really low. And last, you want to utilize all the storage layers that you can get. So we really heavily utilize blob storage to lower the cost for our customers. So everything that you're not using, we are taking off to blob storage. We're saving money, right? Whenever we need to cache something, we'll cache it on the SSD. For the freshness or for the performance layer, we'll cache it on the RAM. So here you have it. You have so now you can go build your own vector database. Let's see kind of the results that we got, and this is really interesting. So we got two things. One is the more data you get in, you get better performance. Okay, meaning I talk to a lot of customers, and I'm working with a lot of customers that are considering, should I put this data in? We have a lot of data sitting there. We don't want to use it, but I don't want to pay for it. Okay, so with serverless, what we see, you don't need to pay for it, and you'll get the extra, you get the extra quality for this one document that someone is querying and needs to get information from. And the second thing is that it levels. When you're doing RAG, it actually levels the kind of the field between the open source LLM and the closed source LLM. Okay, so with good RAG, you can actually use an open source and save money on LLM. So here we are measuring faithfulness, which is the Ragas faithfulness, if you know the metric. If not, Google it. But we're measuring faithfulness as we increase the data set. So as we said, we have around billion embeddings. And each time we are giving the model more. So 10%, 20%, and so on. Okay? So obviously, faithfulness is going up as the data size increases. That's easy. Here we did something more interesting. What we did here is we said, OK, we're going to do, obviously, this data is data that the model was trained on, right? It's common crawl, every LLM today. You're not an LLM if you haven't trained on common crawl, right? So what we did, we actually tried to do a best effort. Try to ask the model, OK, you know what, if you don't know, if you don't have it in the context for some reason, just use your own knowledge, right? So what you see here is obviously, you see the graph is a bit different. There is the dotted line here is showing what is kind of the base behavior. And somewhere around this area, which is around 10% of the data, RAG is already beneficial, even on data that the model was trained on, right? This is kind of a surprising result when we saw it. So again, more data, more accuracy. As I said, it levels the ground. So if you can see, we're measuring the same thing, 4 models. The Mixtral and the Llama 2 was running on Anyscale. And what we did here is we were trying to see, OK, what happens for the RAG versus no RAG? And you can see that with the no RAG, the gap is bigger, especially if you look at, I don't know, GPT 3.5 versus Mixtral. And when you add the RAG, it really basically levels it, OK? So between, what is it, 0.71 to 0.72, OK? It's almost negligible, the difference. Like, your customer's not going to feel it. So to recap a bit on this, we use Ray to scale those embeddings, right? So we did the processing, the loading, everything that Cheng talked about, and got the data into Pinecone. We use Pinecone. We utilize serverless to have this kind of large-scale, enterprise-grade RAG system. And together, you can really scale RAG application to your own data. So before we go, and I want to leave some time for questions, there are a couple of sessions from the Ray team that you want to join. So better check it out on June 13. And if you want to try our products, this is you can take a picture here and go up and sign up. We both have like free tier or credits on the Anyscale platform, and you can try it out. Thank you.